So thank you, Janet. I thank you for inviting me to make this presentation. And you might want to consider my presentation as a outline of a basis for a possible policy and proposal for consideration by the next administration. So I'm sort of looking toward that time period for what I'm going to talk about. And here I talk about CO2 capture technology cost buy-down in EOR applications with alternative financing mechanisms. So I should start off by saying what I mean by technology cost buy-down, which I'll refer to as TCB. And this is carried out after a technology has been demonstrated and before it is undergoing widespread deployment, and it's by far the most expensive part of the whole innovation chain, and it's the one that's been given the least attention. And in my TCB analysis, I will treat only capture options that have the potential for coal to compete with natural gas in the U.S. power market under a carbon policy consistent with limiting global warming to 2 degrees. And what I will show is that the carbon prices implicit in the pursuit of this goal are consistent with what is needed to establish CCS technology in the U.S. market in the near term. And the issue that I think is important here is that if CCS is not launched in the market in the next 5 to 15 years, there is a very big risk that CCS will be taken off the table for consideration as a major carbon mitigation option. And this really has to be done under U.S. leadership. So the policy proposal that I'm going to make here is motivated by the realities that, first of all, according to the IPCC in its 5th assessment report, low carbon global energy futures are probably not feasible without CCS, and global CCS market launch has been stalled at the present time. So a proposal that I'm going to talk about to kickstart the U.S. market launch of promising CO2 capture technologies is to enact a CO2 EOR portfolio standard as one tranche of a national low carbon electricity portfolio standard. And the latter would supplant, the renewable portfolio standard that now exists in 30 states. There would be separate tranches for different low carbon options, and there would be regional strategies to reflect regional resource endowments. Subsidy winners and amounts would be selected by market mechanism, for example, reverse auctions. And I'm going to suggest 2 off-budget mechanisms for financing technology cost buy-down for qualifying technologies. One is a familiar one, which is a wires charge, which is used in the renewable portfolio standard. And the other one is not so familiar, and this is to provide subsidies from what I call an energy security fund for options that provide, in addition to electricity, domestic liquid fuels that displace oil imports. And the Energy Security Fund is made up of new federal corporate income tax revenue streams that arise from the options that provide these new domestic fuels as well as electricity. And then finally here, it's important to note that subsidies can be economically justified by the learning by doing spillovers externality for costly early mover projects that for qualifying technologies. So the CO2 portfolio standard tranche in the National Low Carbon Electricity Standard would mandate that rising amounts of low carbon electricity be provided by plants that capture CO2 and sell it for EOR. And this mandate would also transform the CO2 EOR market into one for which the marginal CO2 supplies come from anthropogenic sources. And this implies that the prices that would result would be considerably higher than the present prices. And in my proposal here, the subsidy amount is determined by the assumption that the levelized cost of electricity with the subsidy has to be as low as the levelized cost of electricity for a new baseload natural gas power plant. Otherwise, the plant won't be built. In terms of the screening process, the candidates that I'm going to select for technology cost buy-down are options that can compete with natural gas when CO2 is stored in deep saline formations, as indicated by an analysis of levelized cost of electricity versus greenhouse gas emission price, when costs are based on what I call scoping study cost estimates. Scoping study cost estimates are the kinds of estimates that are produced by groups like EPRI and NETL. In the case of NETL, we like the baseline power studies, okay? And a warning is that recent experience we have is that first-of-a-kind projects are going to be considerably higher than these costs that are estimated in these scoping studies. And this is one of the reasons why the whole effort has been very much stalled. So if these scoping study cost estimates are underestimate of what it's going to cost to build the next plants, what's the value in thinking about them? Well, they have a very good value in the context of what I'm talking about here. First, if a capture option doesn't pass the test that I've assigned to it here with these scoping study cost estimates, you can forget about that technology. It's not worthwhile to engage it in technology cost buy-down, because if it can't make it with the scoping study cost, it can't make it for early mover cost as well. And then secondly, if a technology option does pass the SSCS test, it becomes a candidate for technology cost buy-down, but still we're not going to know for sure if it really can compete with natural gas combined cycles until we actually build a few plants. So what I'm going to do in terms of the cost is, as I indicated to you, is consider costs that are consistent with this 2-degree global warming scenario. What I show in this graph here is from the IPCC's 5th assessment report, which are price trajectories for alternative trajectories, or for alternative low mitigation scenarios. And I'm only going to focus on the top curve, which is the light blue curve, which is consistent with global warming. And you notice with 2 degree, limiting the global warming to 2 degrees, and you notice that in this particular trajectory here, the greenhouse gas emission price increases from about $60 a ton in 2020 up to over $200 a ton in 2050. And the interesting thing is to look at CO2 emissions prices levelized over the 20-year economic lifetime of new plants coming online in the middle of the next decade, and that's over $100 a ton, as you can see from this graph. And the interesting thing is that those kinds of prices are really needed if we want to launch CCS in the market before 2030. And if we don't do that, CCS is going to be out of the game, I fear. So this is a set of curves, levelized cost of electricity versus greenhouse gas emission price that ranges from $0 to $200 a ton. And the curves are paired. The dashed curves represent CO2 vented, and then the paired solid curves that are color-coded here represent CO2 captured and stored in deep saline formations, and these are based on the scoping study cost estimates. What I want to focus your attention on is that even with carbon capture and storage, which is the solid lines here, you see that the levelized cost of electricity increases with greenhouse gas emission price, which means increases over time. And so if you have to depend on those technologies, prices are going to go up, because they're going to be at some level reflected in these levelized costs of electricity. The next thing I want to call your attention to is the lowest curve here, which is the bright blue curve. That represents natural gas combined cycle, the dash curve vented version, and the solid curve, the CCS version. And you can see that those two curves cross at about $100 a ton, which means that is the minimum price that you need to induce CCS for natural gas combined cycle. I also want to call your attention to the fact that none of the coal options here can compete with natural gas over this entire range of greenhouse gas emission prices greater than $60 a ton, which is what the IPCC says we should be thinking about for 2020. And the reason for this is that, of course, these new coal plant options are casualties of the shale gas revolution in the United States. And I'm not assuming here current natural gas prices for power generators, which in the first 6 months of this year averaged about $3.50 per million BTU. I'm instead using the projected levelized cost of electricity in the annual energy outlook, which is about $6.3 a million BTU. And that is equal to 2.6 times the coal price in the EIA report. And still, as you can see, the current technologies cannot compete with natural gas at any price, at any greenhouse gas emission price. Now, there are things that can be done with advanced technologies, and I think one of the most striking of the advanced technologies that could be pursued is by chemical looping, as Sean pointed out this morning. I'm very excited about chemical looping technology, and the interesting thing is that chemical looping is furthest along in the form of limestone chemical looping that is being pursued very aggressively by Alstom. And so what I put into this is another curve. It's the light green curve, as you can see here, and it's better than all the other coal options with CCS, but it still doesn't beat the natural gas combined cycle at any greenhouse gas emission price. Now, that curve here is for a new plant, a new chemical looping plant, and I've played around with the numbers and convinced myself that it would be extremely cost competitive in retrofit applications, which would be much better than this, and it would be better than natural gas at high greenhouse gas emission prices. So advanced technology is not going to solve the problem for new plants. That's the point that I'm making, as long as these natural gas projections are meaningful. So the question is there anything you can do to make coal competitive with natural gas? And the answer to that is I think there is something that can be done. And that coal biomass co-processing with CCS is key to both the competitiveness for coal in power markets under carbon policy and realization of carbon mitigation goals for energy generally. If you look at the IPCC's fifth assessment report, one of the major conclusions was that many models could not limit likely global warming to 2 degrees C if bioenergy, CCS, and their combination, BECCS, are limited, and that's a high confidence conclusion. And then to extend that to what we want to talk about here, there's a major conclusion that came out of the assessment report of the 2012 workshop on energy supply with negative carbon emissions that came out of the Global Climate and Energy Program at Stanford University, that said that an integrated system of biomass and fossil fuel with capture may be one of the most cost-effective, efficient, and practical ways to move forward in achieving net negative emissions on large stationary sources. And I'm going to explore this with two different options, one of which is I'm going to take that same chemical looping technology and I'm going to add some biomass co-processing into that system. And then I'm going to look at another option that makes liquid fuels as well as electricity. It's something that I call coal biomass to liquids and electricity with CCS. And these kinds of options, which if you co-process enough biomass, can lead to zero or even negative emissions for these systems. And such options are really important for coal, because if you take this 2-degree warming scenario seriously, that means that we have to leave about 5/6 of the coal resources, coal reserves underground. You can't exploit them. And coal reserves are enough for more than 130 years. And so you need to evolve to ways to introduce these kinds of technologies which are completely free of the carbon budget constraint on coal. So this is what happens to that chemical looping option. You see the dark green option here is an option that has 34% biomass. The light green option is one that has it's just coal only. And you can see that at carbon prices of the order of $100 a ton, it becomes, it gives rise to a lower levelized cost of electricity than does natural gas combined cycle. A very important feature of that curve is that it's downward sloping. And that's because of the negative emission rate for this system, and that's a very attractive feature with the expectation of continually rising greenhouse gas emission prices over time. So LCOE goes down over time, so electricity rates go down over time. So it's a very important feature. So this is a schematic of the CBTL CCS system, and I got to take a little bit of time to explain this to you. First of all, notice there are 4 upward pointing arrows that represent carbon flows to the atmosphere, or greenhouse gas emission flows to the atmosphere. And one is up the stack of the energy conversion facility that co-processes coal and biomass to make liquid fuels and electricity with CCS, okay? Some goes up the stack, some goes up out of the tailpipes of the vehicles that consume the synthetic fuels. So there's upstream emissions for biomass and there's upstream emissions for coal. And if the 4 upward pointing arrows equal the downward pointing arrow, which represents carbon extracted from the atmosphere via the growing of 1 ton of biomass to replace 1 ton of biomass that you consume, you're taking CO2 out of the atmosphere. There's some level of biomass co-processing that would lead to net zero greenhouse gas emissions for both electricity and liquid fuels, and it turns out to be 34%, okay? And that's why I chose 34% on that chemical looping example before. I wanted to set the co-processing rates equal. Now, what kind of a system is this? Well, the basic idea is to make syngas first out of coal and biomass via gasification, and then pass the syngas through synthesis reactors to make synthetic fuels, and then burn the unconverted syngas in a combined cycle plant to make electricity. And in order to achieve zero net greenhouse gas emissions, you would have a system that would provide about 70% liquid fuels and 30% electricity. And the question is, why would a power company possibly consider such an option? It is so far from anything that they do at the present time. And there are 2 reasons for it, one of which is, I'll show you in the next slide, very low levelized cost of electricity at high carbon prices, number 1. And then secondly, these plants will have 0 or even negative minimum dispatch costs. So it makes sense to consider building them as must-run baseload power plants, much as the way we design nuclear power plants, okay? And so these things look like they would be very interesting candidates for making baseload power. And another key feature of these is whenever you make liquid fuels, the capture cost is inherently low, because if you capture CO2 upstream of synthesis, you charge that CO2 recovery to the synthesis account and not to the carbon account in the system. So this is technology that can be demonstrated in the near term, and you could do technological cost buy down in the time frame of the middle of this next decade, by 2025, if you can do a demonstration project beforehand. In the case of the chemical looping technology, that cannot be ready for technology cost buyout until sometime after 2030. So if you want to do something soon, gives you a much better option of getting into the market than any of these advanced technologies, which require all of this external development. All of the components in this system are either commercial or ready to be demonstrated. So this is that red curve there is the levelized cost of electricity versus GEP, and you could see that it gives you a stronger downward sloping levelized cost of GEP versus GEP curve than the other technology. And the interesting thing is that systems co-processing less than 30% biomass are ready to be demonstrated right away. You don't have to wait to develop new technology in order to do that. So you could start technology cost buy down by the middle of the next decade. And another important feature of these systems is that the high greenhouse gas emission price would protect investors against the financial risk of low future crude oil prices. And I show that in this graph for a greenhouse gas emission price of $125 a ton. And you can see for that red curve there that all the way down to $40 a barrel, you get attractive internal rates of return in the presence of this very high greenhouse gas emission price. I also show on here a blue curve which represents a zero greenhouse gas emitting system that produces mainly liquid fuels with very little electricity, okay? And you can see that it's much less profitable than the co-production option, and the reasons for that are both scale economies and lower average feedstock cost. So the blue curve represents a zero greenhouse gas emitting system, requires 47% biomass, compared to the co-production case requires 34% biomass. And biomass in these calculations is more than twice as expensive as coal. Okay, so, and the scale economies are quite significant here. So co-production makes a lot of sense, not only from the point of view of the utility, as I mentioned earlier, but also from the point of view of the synthetic fuel producer. Now I'm going to turn to the challenge of technology cost buy-down. I mentioned that these scoping study costs are much too low for early mover projects, and for a first-of-a-kind project, I think that the range of costs for capital and O&M costs are going to be in the range of 1.7 to 2.5 times the scoping study costs. In the case of the Kemper County experience suggests that the cost will be about 2.5 times what the scoping studies estimate. Boundary Dam and Edwardsport experience suggests that the ratio might be something like 1.7. And what I'm going to do is for this CBTLE CCS project, consider two cases, one at the low first-of-a-kind COMC cost ratio of 1.7 in the absence of a comprehensive carbon price. And then in the second case, I'm going to show it for a system with 2.5 times a ratio that is 2.5, but I'm going to assume that you have in place a $100 a ton carbon price for that case. And as far as learning is concerned, for this analysis, I'm going to assume that you have an 11% learning rate, which is at the low end of the experience in the chemical process industry. And since this is chemical process, this might make some sense. But a word of caution is in order here, and that is you cannot know what the learning rate is a priori. So this is just a guess at this point, this 11% learning rate. But there are some positive things you can say about this. One is that the relatively small scales of these systems mean that many of the components can be manufactured in factories where there are good prospects for cost reduction by learning by doing. Uh, and for example, that system, that zero emission system for a 1 million ton per year biomass plant the scale is about 9,000 barrels per day of synthetic liquid fuels and about 250 megawatts of power. But the policymakers should design this technology cost buy-down process in a way that encourages transfer of information from one project to the next so as to facilitate technology cost buy-down. So this is the results of the analysis under those two different conditions. For the 1.7 case, you can see you need to subsidize 2 plants. For the 2.5 case, you need to subsidize five plants. And in order to, in the 2.5 case, in order to become competitive with natural gas for post-2030 time frame, you need to carry out, 14 additional plants besides the 5 subsidized plants without subsidy, just so as to continue going down the cost curve. And this is what the overall economics look like. These are extraordinarily expensive. You see in the 1.7 case, where you have 2 projects, the total amount of subsidy required is $1.4 billion. But the total amount of new federal revenues is over $4 billion over the life of those 2 plants. In the case of the 2.5 FOAC-COMC ratio, you can see that the total cost of buy-down is $5.5 billion, but the total gross new federal revenues are $13 billion. And the 2 points that come out of this are, one is that the government can afford to find out via the proposed technology buy-down process what actual learning rates will be. And that's important because the learning rate must be significant in order to justify these subsidies. And then secondly, positive revenue flows to the Treasury net of subsidies, making this whole process politically feasible using this and the formation of this energy security fund for financing technology buy-down. And then to sum up, the conclusions are that coal-only options for new power plants via advanced technologies are not promising for competing with natural gas combined cycles in the U.S. power market under a carbon constraint, although retrofit versions of these are likely to be competitive with natural gas and would be extraordinarily important for the coal renaissance countries of Asia. And this technology has potentially very low energy penalty of like 10% compared to, say, 25% energy penalty for post-combustion capture. So it would be very attractive in those Asian markets. Secondly, there are promising coal biomass co-processing options that could enable major roles for coal in a carbon-constrained world. And the CBTL CCS option with less than 30% biomass could be ready for early technology cost buy-down by the middle of the next decade if a demo plant can be carried out in the meantime. And the chemical looping option with co-processing here could come in say 5 to 10 years later. And then finally, there's an urgency of getting both the research, development, and demonstration and TCB activity underway to bring promising coal biomass captures into the U.S. market for a domestic reason that is very important, and that is that Ken Kern at NETL did a very important analysis pointing out that there's going to be a huge demand for new baseload power in the United States that is completely unexpected because of the sharp reduction in coal plant capacity factors that can be expected as the age passes 50 years. And he projects that there's going to be something like 140 gigawatts of new baseload capacity needed by 2040 in that time frame. And that Demand is going to be met largely by new natural gas combined cycle plants, and the U.S. will end up having a much less diversified electric power portfolio than at present, unless new coal power options that can compete with natural gas can be brought into the market very, very quickly. And then my final point is that anything that can be made cost competitive in the United States with natural gas is likely to be competitive in most markets throughout the world.